Hey, welcome back, College Chemistry. So today we are looking at box problems. And I know what you're thinking. How many problems can you have about a box? It's only got 6 sides, but okay. We are looking at our gases and how they start to interact. We are looking at things like temperature, volume, pressure, mass of the particles, volume of the particles. All these factors start to interplay and interact as we start to compare our different samples. So there's a lot to think about and a lot to keep track of. And I would argue, I would stake my educational claim that box problems do a really good job of taking all these concepts and putting them into a nice, simple package that then has a lot to think about. And so these box problems are a really good way for us to kind of theoretically work through what's going on in terms of all of our different relationships and their substances. So we're going to work through a couple of these. I want to do a couple with you today, and then I'm going to pause, let you try one, and we'll work through that third one as well. It's just, again, a really nice way to wrap everything up and put it together. I'm going to hide for just a second. That way I can be writing on my screen. You guys know the drill at this point. You guys are such chemistry pros. So containers A and B are identical. They have the same volume is what we're saying when we make that statement. Container A holds 1 mole of nitrogen gas at 298 Kelvin at 1 atmosphere of pressure. Container B holds 1 mole of nitrogen dioxide gas at 298 Kelvin and 760 millimeters of mercury. Compare containers A and B in terms of each of the following. When in doubt, draw it out. Not unlike some of our other problems, when we start to do our dimensional analysis, start with what you know, make it so you can start to work with your values. So we got 2 boxes. I did my best here. Please don't laugh. We're going to pretend that these boxes are identical. They're the same volume. We know that from the information that's been given to us. And we can usually assume that unless our info tells us otherwise. Things get a little tricky if something starts to be different in terms of their volume, but it could happen. Container A holds 1 mole of nitrogen gas, that'd be N2. We know something about those particles. They're going to have a mass on average of 28 grams per mole. We've got a temperature of 298 Kelvin, and we've got a pressure of 1 atm. Cool. Sorry for the scribbles. Hope you can read it. I'll do better on this next one. Box B has 1 mole of nitrogen dioxide gas. Oops, sorry, I should include my 1 there. So we got 1 mole of nitrogen and 1 mole of nitrogen dioxide. Nitrogen dioxide, NO2. We go to the periodic table. Oxygen's 32, so 16 plus 16 is 32, plus another 14 for a total of 46 grams per mole for our nitrogen dioxide. It is at 298 Kelvin and 760 millimeters of mercury. Oh, the pressures are different. Here we had a pressure of 1 atmosphere. Here we've got a pressure of 760. But you know that there are exactly 760 millimeters of mercury for every 1 atmosphere. The 760s cancel. This is 1 atmosphere as well. They tried to trick us, but we didn't let them do it. Cool. A says, compare them. So A says, compare them in terms of their average kinetic energy. Well, remember, we measure the average kinetic energy with the temperature. We know the temperatures. They're both at 298, so they would be the same temperature. Cool. B says the pressure. Oh, we just got done saying that they're both at 1 atmosphere. These are the same pressures. Volume, well, they're the same box. They are identical boxes, so they'd have to have the same volume. D says the mass of the particles. Oh, we already got that. Nitrogen is at 28. Nitrogen dioxide is 46. These are different. This can become important. These are different. Our molecules in box B are greater than our particles in box B. B is heavier than A. Misspoke there for a second. Sorry, getting ahead of myself. Cool. So E says the rate of molecular collisions. This is going back to what we saw in 5.3. We've got 2 particles with the same kinetic energy, the same temperature, but some particles are heavier, the other particles are lighter. Remember that it is an inverse relationship between the mass and velocity of our particles at a constant temperature. Our heavier particles will always be moving on average slower than our lighter particles. The heavier particles move slower than lighter ones. And so we would say the rate of molecular collisions is going to be greater for the higher particles, our faster particles. So E, our particles in A are going to hit more frequently than our particles in box B. And that is because the speed is different. So G is kind of similar. I'm going to hop down for just a second. A is moving faster than B. It's an inverse relationship. The lighter the particles, the faster they will be going at the same temperature. Temperature, we said already to be the same because it is the same as our measure on A. Cool. Ooh, there's a lot to think about when it comes to these boxes. Let's try another one. Let's make sure we're doing okay. And we've got some good examples to be looking at. Our second one here. So we got chlorine. Oh, the boxes are truly identical for this one. We got chlorine. Oop, gotta hit the button. There we go. We got Cl2 for both the particles. We got 760 millimeters of mercury versus 380. They're in the same unit, so we can compare them directly this way. And then we got 325K, 325K. Remember that Kelvin measures the temp. It helps you label it. Millimeters of mercury measures the pressure. Cool. Number one, the number of molecule. Oh, okay. Ooh, starting right off the bat with a hard one. Let's think about what we know. We know that we have identical particles. Let me draw them here. We have identical particles in both of the boxes. Their masses are the same. They're also at the same temperature. Oh, so they're traveling at the same average molecular kinetic energy and the same average molecular velocity. These, I'm jumping ahead a little bit. We know these are the same. The kinetic energy is the same because the temp is the same. And the velocity would also have to be the same because they're the same particles at the same temperature. Oh, they have the same mass. Okay. But there's a problem. The pressures are different. Well, if you remember, there's kind of three ways that we can start to be interacting with our pressure. We can change, in order to affect the pressure, we can change the temperature, we can change the volume, or we can change the number. Sorry, that says moles. That was rude. We can change the number of molecules or particles in the box. You do this all the time. Anytime you have a flat tire, you pump more air in and now your pressure goes up because you've added more particles. They're going to collide more often. And so if everything is the same here, except the pressure, well, that must mean that the number of molecules is different. One of our boxes must have more particles than the other. Well, which one has a greater pressure? It's A. A must have a greater number of chlorine than box B in order for there to be more collisions and more measured pressure. That gives us our answer for 4 as well. The number of collisions per second must be different because we have a different pressure. A would have to be greater than B because you got more particles bouncing around in your box. They're going to collide more frequently, increasing the pressure with everything else being held equal. Oh my goodness. Sorry, I'm being a little braggart here. It's kind of a lot to think about. Let's look at another one, give you an example that you can try, and then we'll kind of work on through. So here's the third one for you to think about. Go ahead, pause it. Try 1 through 4. If they're the same, great. If they're different, which one is greater? Which one is greater? Hopefully you paused it, gave this a shot. There's a lot to analyze here. We got helium, which is just our He, average time of mass of approximately 4 grams per mole. Hydrogen is H2. Watch out for your diatomic. It's going to be 4.016 grams per mole. Oh, that is mean. Oh, but there's 2 moles worth. Oh, okay. Oh, okay, that's great. Let's take a look at these boxes. Number 1 says the average molecular kinetic energy. Well, we measure that with the temperature. Temperature is the same. We got the same temp here. The mass of the whole container. So if we were to take box A, put it on a balance, box B, put it on a balance, which one is going to have a greater mass? Well, they both have a mass approximately of 4. But that's per mole. We got 2 times the moles in the second box. 4 times 2 is going to be 8 grams approximately for the number of moles in there, whereas this one is just going to be 4 grams. So for number 2, they are going to be different. B, box B is going to be heavier or more massive than box A. Speed of the molecules, ooh, it's close, right? It's really close, but technically helium is just a little bit lighter than our particles in box B. And as a result, they're going to be different. Our particles in box A would have to be moving just a little bit more speedy than box B. The lighter the particle, the faster it is moving at the same temperature. Lighter the particle, the faster it's moving. Inverse relationship. Cool. Rate of collisions. Ooh, this one, oh, it's hard to think about. Rate of collisions, we measure collisions with the pressure. Measure it with the pressure. Here we have the same pressure, right? This is going to be the same, but wait, how can that be? We have twice the number of particles in box B than we do in box A. And they're traveling at almost the same speed, at almost the same mass. Well, how could that be? We weren't told this, but the boxes must be different to facilitate this same pressure. A lot to think about. If we were to be real mean, we would ask then a follow-up question about the volume. In this instance, box B would have to be bigger than box A in order for the pressures to be the same, given that we have twice the number of particles of moles in box B compared to box A. Cool. It's a nice way to kind of think about all these different variables all together. Hopefully this is making sense. We'll be coming back. We'll be practicing some more of this. It's just, again, real nice to be kind of working through some of these types of calculations. Thanks. Have a great day.